Welcome back. In this video, we're going to continue the problem we were just talking about in the video which preceded this. We're going to find the principal unit normal vector for the helix, pictured here, and we're going to describe how that normal vector is pointing. So we were dealing with a helix, which was defined as the vector r equals a cosine t times I plus a sine t times j plus btk. And if we want to find the principal unit normal vector, we need to know how n is defined. N is defined as the derivative of the unit tangent vector divided by its magnitude. And so that's how we find any unit vector, right? This is the principal unit normal vector. So any unit vector is going to be that vector divided by its magnitude. Now remember, the normal vector is orthogonal or perpendicular to our unit tangent vector. And because the unit tangent vector is a constant length vector, it's only telling us direction, we know that the derivative of that constant vector is going to produce a new vector which is orthogonal. Therefore, it makes sense why that derivative of the unit tangent vector is inside the definition for our principal unit normal vector. So I've brought in here the derivative of the unit tangent vector and as well as its magnitude that we calculated in the previous video. I'm not going to go through the calculation of those again. But if we want to find our principal unit normal vector, that's going to be this, the derivative of the unit tangent vector divided by its magnitude. So I've got negative a cosine t I plus negative a sine t j over the root a squared plus b squared, then divided by a over square root of a squared plus b squared. We should see pretty easily that those denominators are going to cancel. I'll write this out in two steps though. So that leaves me with negative a cosine t I plus negative a sine t j over a. And now, in case it wasn't before, it's easy to see these a's cancel. And my principal unit normal vector is equal to negative cosine t I minus sine t j. So here we have the calculation for our principal unit normal vector. A couple of things to note, since this is only in two space with I and j, that n is always parallel to that xy plane. It's a circle in a sense, or on the edge of a circle, on the edge of that circle radius, whatever a is, pointing in. Since both of these values are negative, it's going to be pointing in, which makes sense because we said that the normal vector is always pointing in towards the curve or inside the concave portion of our vector. As always, email me if you have any questions.